So let's talk about the parts of an atom. The nucleus is the positively charged center of an atom. The nucleus is where most of the mass of an atom is. The electrons that are around the nucleus are actually fairly small. So what's in the nucleus makes up most of an atom's mass. Even though the nucleus is most of the atom's mass, it's only about 1/10,000th the size of the atom. So it's fairly small in terms of the area that it takes up, but it contains most of the mass. So the nucleus contains the protons and the neutrons. The protons are the positively charged subatomic particles, and the neutrons are the neutral subatomic particles. Around the nucleus, we have the electrons, which are negatively charged particles. So the atomic number is the number of protons that are in an atom. The atomic number is what determines the identity of the atom. If you change the number of protons, you've changed what element you're talking about. The mass number is the total number of protons and neutrons in the nucleus. So if we add together protons plus neutrons, we have mass number. For example, if we look at the hydrogen atom on the left here, hydrogen has an atomic number of 1, and this particular hydrogen atom does not have any neutrons. So its atomic number would be 1 because it has 1 proton, and because it doesn't have any neutrons, 1 plus 0 gives it a mass number of 1. If we look at this helium atom here, helium has 2 protons, and this helium atom has 2 neutrons. So 2 protons means it has an atomic number of 2. 2 plus 2 gives it a mass number of 4. So if we look at the protons, neutrons, and electrons and their actual masses, you'll see electrons are pretty small compared to protons and neutrons here. So sometimes we express this in terms of relative mass rather than in terms of their actual masses. When we express things in relative mass, we measure them in terms of AMU, or atomic mass units. And those are units that we use to express the relative masses of things like atoms and subatomic particles. So the way we do that is we divide all of these masses by the mass of a proton or the mass of a neutron, since they're the same mass. If you divide 1.67 times 10 to the -27th by itself, you get 1. If you divide 9.11 times 10 to the -31st by 1.67 times 10 to the -27th, we get a number that's so small we can essentially say it's 0. So we say protons and neutrons have a relative mass of 1, and electrons have a relative mass of 0. Protons have a charge of +1, neutrons have a charge of 0, and electrons have a relative charge of -1. So let's look at a few examples here. If we look at a sulfur atom, sulfur has an atomic number of 16, and this particular sulfur atom has a mass number of 32. So since atomic number is the number of protons, if it has an atomic number of 16, that means that we've got 16 neutrons. Mass number is protons plus neutrons, so if we subtract the mass number minus the number of protons, we will get the number of neutrons. So our mass number is 32. We subtract 16. That equals 16, which is our number of neutrons. And since this atom is neutral, the number of electrons, which are our negative particles, has to equal our number of protons. So if we have 16 protons, we have to have 16 electrons. Now, what if you're not given the atomic number? Well, we can look that up on the periodic table. The atomic number is the whole number that's usually written above the element. So if you look up nickel on the periodic table, what you'll find is that it has an atomic number of 28, which means that it has 28 protons. If we take the mass number 57 and we subtract off 28, that will give us the number of neutrons. That comes out to 29. So we have 29 neutrons. Since this nickel is neutral, if it has 28 protons, that means it has 28 electrons. If we look at the next row, we have nickel again, but this time we have a mass number 59. So we know that its atomic number is 28, which means it has 28 protons. 59 minus 28 gives us 31 neutrons. And since this is neutral, it must have a number of electrons that's equal to its number of protons. Now let's look at a couple of examples that are charged. So we know that sulfur has an atomic number of 16, which means it has 16 protons. We also know that this particular atom with a mass number of 32 is 16 neutrons. But we now have a 2 negative charge. So remember that electrons are our negative particles. If we have a 2 negative charge, that means we have to have 2 more negative particles than we do positive particles. So if we have 16 protons, that means that we have 18 electrons. So remember that the negative or the positive refers to the charge, not to addition or subtraction. Okay, so don't confuse that. We have nickel here with a 2 positive charge, so we already figured out that this atom that has a mass number of 59 has 28 protons and 31 neutrons. If it has a 2 positive charge, that means that we have 2 more positive particles than we do negative particles, which means that if we've got 28 protons, we only have 26 electrons. So we saw on this exercise that we had 2 examples of nickel that had different mass numbers. And when we calculated how many neutrons they had a different number of neutrons. We call these atoms that have the same number of protons but a different number of neutrons isotopes. So remember, we can't change the number of protons. That would change the identity of the element. But we can change the number of neutrons, and that gives us a different isotope of the element. The way that we write symbols for isotopes is we write the elemental symbol here, which we just have X here in this example, but we would write whatever our element is there. The number at the top is our mass number. So our mass number here is represented as A. Remember, mass number is the total number of protons and neutrons. And then what we have labeled as Z here is where we write the atomic number. which is the number of protons in the nucleus. So let's look at an example here. If we take an element such as uranium, so most elements do have 2 or more isotopes, which means they have the same atomic number but different mass numbers. So if we take uranium, we see here they both have an atomic number of 92 because they're both uranium, but they have different mass numbers. One has a mass number of 235 and the other has a mass number of 238. So if we take the first example, 235 minus 92, that isotope of uranium has 143 neutrons. If we look at the other isotope, 238 minus 92 equals 146 neutrons. So they both have 92 protons, but one has 143 neutrons, whereas the other one has 146 neutrons. So let's take a look at an example here. We want to use this format to write the symbol for a nuclide that has 15 protons and 17 neutrons. So if we look up on the periodic table and find which element has 15 protons, that would be phosphorus. And then we write 15 down here because that's our atomic number. Up top, we want the mass number. So 15 protons plus 17 neutrons gives us a mass number of 32. So we would write it with 15 at the bottom and 32 at the top. Now, if you look at the periodic table, you'll see another number written up under a lot of elements. On most periodic tables, it's up under the element, although sometimes you will see it above. And you'll notice that that number is a decimal. The reason that number is a decimal, because you can't have a part of a proton or a part of a neutron. They're all whole particles. But the reason it's a decimal is that it is a weighted average of all of the isotopes. So let's look at a couple of examples here how we would calculate that. So we have neon here, which has a mass number given to us in AMU, and then we have its natural abundance. So to calculate the average atomic mass of neon, what we would do is we convert the percentages to a decimal by moving the decimal over 2 places. And then we take our mass in AMU. So if we take our first isotope and we multiply that by and then we're going to, for our second isotope, do the same thing. Oops. And then for our last isotope, And for these, what I'm going to tell you to do is to keep the same number of decimal places that you're given in the mass when you calculate your final answer here. So, if you multiply 19.9924 by the percentage as a decimal and do that for each of your other isotopes, then what you should come up with is, when you add these together, 20.1799 AMU. Let's look at another example here. What is the average atomic mass of magnesium given the three isotopes below? So we're going to do the exact same thing that we did with neon. So we multiply the mass of each one by its percentage as a decimal. And if you multiply those together and add them up, and you should come up with 24.3050. Let's see, we want 1, 2, 3, 4, 5, 6. Decimal places. So we come up with 24.305052 AMU. Okay, so we're going to stop here and we'll get some more practice with this in class.